Welcome to Whispering Atom, where the deepest mysteries of our universe unfold in gentle whispers, and science becomes a peaceful companion for your evening rest. I'm so grateful you've chosen to join me tonight as we embark on a journey that will take us not across distant galaxies or through vast oceans, but inward, deep into the heart of our own planet, to explore one of the most profound and quietly beautiful processes happening beneath our feet right now. As you settle in wherever you are in this wide world, I'd love for you to share where you're listening from tonight and what time it shows on your clock. Are you nestled in bed as the evening settles around you? Perhaps watching from a quiet corner of your home where the day's last light filters softly through your windows? Maybe you're somewhere where dawn is still hours away, wrapped in the gentle embrace of nighttime. Take a moment, if you feel inclined, to let us know in the comments below where you are and what time your corner of the world is experiencing right now. There's something wonderfully grounding about knowing we're all here together, scattered across this rotating planet, united in our curiosity about the very forces that keep our world spinning beneath us. Now, get comfortable. Let your shoulders drop just a little. Adjust your pillows, perhaps pull that blanket closer around you. Take a slow, deep breath and feel yourself settling into this moment, this quiet space we're creating together. Tonight, we're going to explore something that's happening right now, this very second, deep beneath the ground you're resting on, a gentle, almost imperceptible cooling that's been occurring for billions of years and will continue long after we're gone. We're going to discover what really happens when Earth's core cools slightly, and how this most gradual of all planetary processes shapes everything from the magnetic field that protects us to the very rotation of our world. Imagine, if you will, that you could somehow journey to the very center of our planet, not with the violence of digging or drilling, but with the gentle ease of thought, sinking slowly through layer after layer of rock and metal until you reach the heart of the world that cradles all life as we know it. It's a journey of nearly 4,000 miles downward, through realms of pressure and temperature that challenge our ability to comprehend. Yet it's a journey that reveals some of the most beautiful and quietly profound processes in our solar system. As we begin this peaceful descent in our imagination, we pass first through the familiar solid ground beneath our feet, the crust of the Earth, that thin shell of rock that forms the continents and ocean floors. This crust, which seems so permanent and unchanging from our human perspective, is actually just the thinnest skin on our planet, proportionally thinner than the skin of an apple. Beneath this familiar surface lies a world of slow motion, of patient transformation, of forces so gradual and persistent that they operate on timescales that make human history seem like a brief flicker. Deeper we go through what geologists call the mantle, a vast realm of hot rock that flows like thick honey over millions of years. Here, temperatures rise steadily as we descend, and the rock around us becomes increasingly plastic, flowing in great convection currents that carry heat from the depths toward the surface in cycles that last hundreds of millions of years. The mantle is patient beyond human comprehension, moving continents like leaves on a slow river, creating mountains and ocean basins through processes so gradual that entire species evolve and disappear in less time than it takes for these deep currents to complete a single circulation. But we're traveling deeper still toward the true heart of our planet, where temperatures and pressures reach conditions that exist nowhere else in our solar system except perhaps in the cores of other worlds. As we pass through the transition zone where the mantle meets the core, we encounter one of the most remarkable boundaries in nature. The place where solid rock gives way to liquid metal, where the familiar chemistry of surface minerals transforms into something altogether more fundamental. And then, at last, we arrive at our destination. The outer core of the Earth, a sphere of molten iron and nickel that extend from about 1,800 miles beneath the surface to just over 3,000 miles down. This is a realm of liquid metal at temperatures that exceed the surface of the sun, where pressures are millions of times greater than the air we breathe, where the very atoms are compressed into configurations that don't exist anywhere in the surface world. The outer core is not still or quiet despite its depth. Instead, it's a dynamic, flowing realm where liquid metal moves in complex patterns driven by the slow cooling of the planet and the rotation of the Earth itself. These movements are gentle by the standards of their environment. No violent explosions or dramatic events. But they carry consequences that reach all the way to the surface and beyond, shaping the magnetic field that protects our atmosphere, influencing the length of our days, and connecting the deepest interior of our planet to the space environment around us. This liquid metal ocean exists at temperatures that hover around 10,000 degrees Fahrenheit, hot enough to vaporize any surface material instantly, yet cool enough to remain liquid under the enormous pressures of the deep Earth. It's composed primarily of iron, that most common of metals, mixed with smaller amounts of nickel and traces of other elements that have settled into the planet's center under the influence of gravity over billions of years. The iron that flows in the outer core isn't the familiar iron of surface rocks or metal tools. Under the extreme conditions of the deep Earth, this iron takes on properties that would seem almost magical to surface dwellers. It conducts electricity with extraordinary efficiency, flows with the ease of water despite being far denser than any surface liquid, and responds to magnetic fields in ways that create feedback loops capable of generating and sustaining magnetic fields that extend far into space. But perhaps most remarkably, this entire vast ocean of liquid metal is slowly, gently, almost imperceptibly cooling. The Earth formed hot, born from the collision of countless smaller bodies in the early solar system, and it has been cooling ever since. This cooling process operates on timescales so vast that human civilization represents just the tiniest moment in the planet's thermal history, yet it's a real and ongoing process that shapes every aspect of our planet's behavior. The cooling happens through heat loss to space, a process as gentle and inevitable as the warming of your hands by a fire, but in reverse. Heat generated by the radioactive decay of elements deep in the Earth, heat left over from the planet's formation, heat created by the friction of the liquid metal's own motion. All of this thermal energy slowly makes its way toward the surface and eventually radiates away into the cold of space. This cooling process isn't uniform or simple. Like a pot of thick soup cooling on a stove, the Earth loses heat through complex patterns of convection, conduction, and radiation. The liquid metal of the outer core participates in vast circulation patterns, carrying hot material from the depths toward the boundary with the mantle, where it transfers its heat and then sinks back down to be reheated and begin the cycle anew. But what happens when this cooling accelerates slightly, when the temperature of the outer core drops by just a few degrees over the course of thousands or millions of years? The changes begin subtly, almost invisibly, but they propagate through the entire system of our planet like ripples spreading from stone dropped into still water. The first changes occur at the molecular level, in the behavior of individual iron atoms as they respond to the slightly lower temperatures. Iron, like all metals, expands when heated and contracts when cooled. But in the extreme environment of the outer core, these thermal effects are amplified and complicated by the presence of enormous pressures and magnetic fields. As the temperature drops, the liquid iron becomes slightly denser, slightly more viscous, slightly less willing to flow in the rapid currents that characterize the fully molten state. This isn't a dramatic change. We're talking about alterations that might amount to a fraction of a percent over thousands of years. But in a system as finely balanced as the Earth's core, even tiny changes can have far-reaching consequences. The viscosity change is particularly important because it affects how easily the liquid metal can move in response to the forces that drive convection. Slightly thicker, slightly more resistant to flow, the cooling iron begins to move in subtly different patterns. Convection currents that have maintained steady patterns for millions of years start to shift and reorganize as the changing physical properties of the metal create new preferences for where and how the heat transport occurs. These shifting convection patterns don't just redistribute heat. They also reorganize the motion of electrically conducting metal that generates Earth's magnetic field. The magnetic field isn't created by a permanent magnet buried in the Earth's core, but rather by the motion of conducting liquid metal acting like a dynamo, converting mechanical energy into magnetic energy through complex electromagnetic processes. When the convection patterns change, the dynamo changes with them. The magnetic field strength might increase or decrease, the orientation of the magnetic poles might shift, or the overall structure of the field might reorganize into new configurations. These changes happen gradually, over timescales of thousands to millions of years, but they represent some of the most profound alterations that a planet can undergo. For those of us living on the surface, these deep changes might seem impossibly remote and irrelevant to daily life. After all, we can't see or feel the motion of liquid metal thousands of miles beneath our feet, and the cooling process operates so slowly that thousands of human generations might pass without anyone noticing a difference. But the effects are real and measurable. Scientists studying the Earth's magnetic field have discovered that it's constantly changing, strengthening and weakening, shifting its orientation, sometimes even reversing completely so that magnetic north becomes magnetic south and vice versa. These changes reflect the ongoing evolution of conditions in the outer core, the slow response of the iron dynamo to the planet's gradual cooling. The magnetic field changes affect more than just compass directions. Earth's magnetic field extends far into space, creating a protective bubble called the magnetosphere that deflects charged particles streaming from the sun. When the field strength changes, the effectiveness of this protection changes too, potentially altering the amount of cosmic radiation that reaches the surface and influencing everything from climate to the evolution of life. But we're getting ahead of ourselves. For now, as we rest here in our imagination at the heart of the Earth, surrounded by an ocean of liquid metal at temperatures that exceed the surface of the sun, we can simply appreciate the profound beauty of this hidden realm. The outer core represents one of the most stable and long-lasting features of our planet, a vast reservoir of heat and motion that has been operating continuously for over 4 billion years. The liquid iron that surrounds us has been flowing in these depths since before life appeared on the surface, before the first oceans formed, before the first atmosphere developed. Individual iron atoms have been cycling through convection patterns for eons, participating in the generation of magnetic fields that have protected our planet through ice ages and warm periods, mass extinctions and evolutionary radiations, the rise and fall of mountain ranges, and the opening and closing of ocean basins. Yet this ancient, stable system is also dynamic and responsive. The cooling that we're exploring isn't a sign of the Earth winding down or dying, but rather a natural part of planetary evolution, a slow transition from one thermal state to another that will continue for billions of years into the future. As we float here in this imaginary space at the center of our world, we can feel ourselves connected to processes that operate on timescales beyond human comprehension. The heat that surrounds us in the outer core is the same heat that drives volcanic eruptions at the surface, that moves continents and builds mountain ranges, that creates the magnetic field that guides migrating animals and protects our atmosphere from the solar wind. The cooling we're studying represents one of the most gradual and patient processes in nature, a planetary-scale example of how the universe tends toward thermal equilibrium, how hot things slowly give up their heat to cooler things until everything reaches the same temperature. But in the case of Earth's core, this process is so slow that it will continue long after our sun has aged and changed, long after the surface of our planet has been transformed by forces we can't yet imagine. The gentle nature of core cooling stands in beautiful contrast to the dramatic events we often associate with geological processes. There are no earthquakes in the outer core, no volcanic eruptions, no sudden shifts or catastrophic changes. Instead, there's just the patient circulation of liquid metal, the gradual transfer of heat from hot regions to cooler ones, the slow response of physical properties to changing temperatures. This peaceful, gradual nature makes core cooling one of the most profound examples of deep time in action. While human events unfold over days, years, or centuries, and even major geological processes like mountain building occur over millions of years, core cooling operates on timescales measured in billions of years. It's a process that connects the formation of our planet to its distant future, spanning geological eras like a slow heartbeat that marks the passage of planetary time. As we prepare to explore the specific effects of this cooling in the chapters ahead, we can rest in the knowledge that we're studying one of the most fundamental and stable processes on our planet. The outer core beneath us has been cooling slowly and steadily for longer than complex life has existed on Earth, and it will continue cooling long after humans have evolved into forms we can't yet imagine, or perhaps long after we've traveled to other stars entirely. The beauty of this process lies not in its drama or its speed, but in its patient persistence, its gentle inevitability, its deep connection to the most fundamental physical laws that govern how energy flows through the universe. As we journey deeper into understanding what happens when Earth's core cools slightly, we're exploring not just planetary science, but the profound question of how change occurs in systems so vast and stable that they seem almost eternal from our human perspective. In the chapters that follow, we'll trace the effects of this cooling from the molecular level to the planetary scale, discovering how the slightest changes in temperature deep beneath our feet can eventually influence everything from the strength of the magnetic field to the length of our days. But for now, we can simply rest here in this place of liquid metal and gentle heat, feeling ourselves connected to the deepest rhythms of our planet, the slow and patient processes that have been shaping our world since long before the first sunrise, and will continue long after the last sunset fades into the cosmic dark. Now that we've found our peaceful place at the heart of our planet, suspended in imagination within this vast ocean of liquid metal, let's take time to really understand what's happening around us in this remarkable realm. The outer core isn't a still, quiet place despite its incredible depth and the crushing pressures that surround us. Instead, we're witnessing one of the most elegant and persistent forms of motion in the natural world, a gentle stirring that has continued uninterrupted for over 4 billion years, creating patterns of flow so vast and slow that they dwarf any movement we might observe on the surface. The liquid iron that surrounds us moves in response to forces that operate on scales both impossibly large and incredibly subtle. The primary driver of this motion is heat, the same fundamental force that causes water to circulate in a pot on a stove, but operating here under conditions so extreme that the familiar rules of surface behavior are transformed into something both alien and beautiful. Deep beneath us, closer to the very center of the Earth, lies the inner core, a solid sphere of iron and nickel that exists at temperatures even higher than the liquid metal around us, but remains solid due to the enormous pressure at the planet's center. This solid inner core acts like a massive heating element, slowly releasing heat that was trapped during Earth's formation over 4.5 billion years ago, along with heat generated by the ongoing radioactive decay of elements scattered throughout the planet's interior. This heat doesn't stay where it's generated. Like all thermal energy, it seeks to move from hot places to cooler places, following the fundamental physical law that drives all heat transfer throughout the universe. In the liquid iron of the outer core, this heat transfer occurs through convection, the same process that creates weather patterns in our atmosphere and ocean currents in our seas, but here operating in a medium thousands of times denser than water and at temperatures that would instantly vaporize any surface material. The convection process in the outer core creates patterns of motion that are breathtakingly beautiful in their complexity and scale. Imagine columns of hot liquid iron, each hundreds of miles in diameter, rising slowly from the depths like invisible thermal chimneys. These columns carry enormous amounts of heat energy upward, moving at speeds that seem glacial by human standards, perhaps a few millimeters per year, but representing the transport of more energy than all of human civilization has ever produced. As these columns of hot metal rise through the outer core, they eventually reach the boundary between the core and the mantle, a transition zone where the liquid iron meets the solid rock above. Here, the thermal energy is transferred to the overlying mantle rock, and the slightly cooled iron begins its long journey back down toward the depths, sinking in broad, gentle downwellings that complete the convection cycle. But this isn't simple, uniform motion. The convection in the outer core is complicated by the rotation of the Earth itself, which introduces forces that twist and shape the rising and falling columns of liquid metal into complex helical patterns. The Coriolis effect, the same force that influences weather patterns on the surface, operates here with profound consequences, creating columns that spiral as they rise and fall, generating the twisted, intertwining motions that are essential for creating Earth's magnetic field. These spiraling convection patterns don't exist in isolation. They interact with each other, creating interference patterns, reinforcements, and cancellations that generate an incredibly complex three-dimensional flow structure throughout the entire outer core. It's like a vast, slow-motion symphony where individual instruments are columns of moving metal hundreds of miles across, playing notes that last for thousands of years, creating harmonies and rhythms that span geological ages. The electrical conductivity of a liquid iron adds another layer of beauty and complexity to this motion. The outer core isn't just a flowing liquid, it's a flowing electrical conductor. And when electrical conductors move through magnetic fields, they generate electrical currents. These currents, in turn, create new magnetic fields, which influence the motion of the conducting liquid, which generates more currents, creating a self-sustaining electromagnetic dynamo that has operated continuously for billions of years. This dynamo process is remarkably similar to the electrical generators that power our surface civilization, but operating on a scale that dwarfs any human technology. The outer core is essentially a planetary-scale electrical generator, converting the mechanical energy of convective motion into magnetic energy that extends far beyond the Earth itself, creating the magnetosphere that protects our planet from the constant stream of charged particles flowing from the sun. The specific patterns of convection in the outer core determine the characteristics of the magnetic field that reaches the surface. When the convection is vigorous and well-organized, the magnetic field is strong and stable. When the convection patterns become more chaotic or less energetic, the field may weaken, fluctuate, or even reverse its polarity entirely. These changes in the magnetic field provide a direct window into the deep processes occurring thousands of miles beneath our feet. But what happens when the overall temperature of this system begins to change? When the gentle cooling that has been occurring since the Earth's formation causes the average temperature of the outer core to drop by just a few degrees over the course of millions of years. The changes begin with the fundamental physical properties of the liquid iron itself. As temperature decreases, the viscosity of the liquid metal increases. This is a universal property of liquids. They become thicker and more resistant to flow as they cool. In the outer core, this means that the liquid iron becomes slightly less willing to move in response to the thermal forces that drive convection. The changes are subtle at first, perhaps a fraction of a percent increase in viscosity over thousands of years. But in a system as finely balanced as the Earth's core dynamo, even tiny changes can have profound consequences. The increased viscosity affects the convection patterns in complex ways. Some convection columns may become less vigorous, moving more slowly as the thicker liquid resists the thermal forces trying to drive the circulation. Others may change their preferred diameter or spacing as the balance between thermal driving forces and viscous resistance shifts to favor different scales of motion. These changes in convection don't happen uniformly throughout the outer core. Different regions may respond differently to the cooling, depending on their local thermal conditions, their distance from the inner core boundary, and their position relative to the major convection patterns. This leads to a gradual reorganization of the flow structure, as some convection columns strengthen while others weaken, and new patterns of circulation emerge to accommodate the changing physical properties of the liquid metal. The reorganization of convection patterns directly affects the electromagnetic dynamo that generates Earth's magnetic field. The magnetic field isn't created by the simple motion of liquid metal, but by the specific patterns of that motion. The way the flowing iron creates electrical currents, the way those currents interact with existing magnetic fields, the way the resulting electromagnetic forces feed back to influence the motion itself. When cooling changes the convection patterns, it changes the dynamo. The magnetic field generated by the reorganized flow may be stronger or weaker than before, may have a different orientation, or may fluctuate more or less than it did under the previous thermal conditions. These changes propagate upward through the mantle and eventually reach the surface, where they can be detected by sensitive instruments that measure the strength and direction of the magnetic field. The cooling process also affects the rate at which heat is transported from the inner core to the core mantle boundary. As the liquid iron becomes more viscous and the convection becomes less efficient, heat transport may slow down, causing temperatures to rise slightly near the inner core and drop near the core mantle boundary. This temperature redistribution can have its own effects on the convection patterns, creating feedback loops that either amplify or dampen the initial changes caused by the overall cooling. One of the most fascinating aspects of core cooling is how it affects the growth of the inner core itself. The boundary between the liquid outer core and solid inner core isn't fixed. It's a dynamic interface where liquid iron solidifies as heat is removed and temperatures drop. As the outer core cools, this boundary slowly moves outward, with liquid iron crystallizing into solid metal and adding to the mass of the inner core. This process of inner core growth is remarkably slow by human standards, with the radius increasing by perhaps a millimeter every 1,000 years. But over geological time, this gradual solidification has profound effects on the dynamics of the outer core. As the inner core grows, the volume of liquid metal in the outer core decreases, which can change the preferred scales and patterns of convection. The growing inner core also releases latent heat as the liquid iron crystallizes, adding an additional heat source to the thermal budget of the outer core. This latent heat can help sustain convection even as the overall system cools, creating complex interactions between cooling, solidification, heat release, and flow patterns that make the evolution of the core a richly interconnected process. The chemical composition of the outer core also changes as cooling progresses. As iron crystallizes to form the growing inner core, lighter elements that were dissolved in the liquid metal are left behind, gradually increasing their concentration in the remaining liquid. These lighter elements, which may include sulfur, silicon, oxygen, or hydrogen, can significantly affect the physical properties of the liquid metal, including its density, viscosity, and electrical conductivity. The changing composition creates additional driving forces for convection, as regions with different concentrations of light elements develop different densities and become buoyant or dense relative to their surroundings. This compositional convection can interact with thermal convection in complex ways, sometimes reinforcing the thermal patterns and sometimes creating competing flow structures that lead to more chaotic or variable behavior. As we float here in this imaginary space within the outer core, we can sense the incredible complexity of the processes occurring around us. The liquid iron that surrounds us isn't just moving in simple circulation patterns, but is participating in a vast, interconnected system where thermal effects, electromagnetic forces, rotational influences, and chemical changes all interact to create one of the most sophisticated natural phenomena on our planet. The gentle stirring we're witnessing isn't random or chaotic, despite its complexity. Instead, it follows physical laws that operate with the same reliability and predictability as any other natural process, but on scales of space and time that challenge our human ability to comprehend. The convection patterns around us have been refined through billions of years of continuous operation, shaped by the fundamental forces of physics into configurations that efficiently transport heat, generate magnetic fields, and maintain the thermal balance that keeps our planet's interior in its current state. The cooling that we're exploring doesn't disrupt this elegant system, but rather guides its gradual evolution toward new configurations that are equally stable and beautiful, but adapted to slightly different thermal conditions. The outer core has experienced many such transitions throughout Earth's history, always finding new patterns of motion that accommodate changing conditions while maintaining the essential functions of heat transport and magnetic field generation. The timescales involved in these transitions are so vast that they provide a profound perspective on the nature of change itself. While human societies rise and fall, species evolve and go extinct, and continents drift across the surface, the stirring of the outer core continues with a patience and persistence that connects the formation of our planet to its distant future. The cooling we're studying is part of the longest continuous process on Earth, a gentle transformation that began when our planet first formed and will continue until the last heat has escaped to space billions of years from now. As we prepare to explore the specific effects of this cooling on the magnetic field in the next chapter, we can appreciate the remarkable stability and resilience of the system we're studying. The outer core represents one of the most reliable and long-lasting mechanisms in the natural world, a planetary-scale engine that has operated without interruption for longer than complex life has existed on the surface. Yet this ancient stability doesn't mean stagnation. The gentle stirring below responds and adapts to changing conditions with the same patient persistence that characterizes all deep Earth processes. The cooling we're exploring is part of this adaptive response, a natural progression toward thermal equilibrium that will unfold over timescales so vast that they encompass entire chapters of planetary evolution. In this realm of liquid metal and gentle heat, we find not just the mechanical operation of convection and dynamo processes, but a profound example of how the universe organizes matter and energy into complex, self-sustaining systems. The stirring of the outer core represents one of the most beautiful expressions of physical law in action, where simple principles of heat transfer and electromagnetic induction combine to create phenomena of breathtaking complexity and enduring stability. As we rest here in the heart of our planet, we can feel ourselves connected to these deep rhythms of thermal circulation, electromagnetic generation, and gradual cooling that have been shaping our world since long before the first oceans formed on the surface. The gentle stirring that surrounds us is both ancient and eternal, a process that links us to the formation of our solar system and extends forward into a future where our planet will still be slowly cooling long after our sun has aged and changed into something we can barely imagine. Here in the heart of our planet, surrounded by the gentle circulation of liquid iron at temperatures that exceed the surface of the sun, we're about to witness something remarkable. The subtle but profound changes that occur when this ancient system experiences even the slightest cooling. The temperature changes we're exploring aren't dramatic by human standards. We're talking about decreases of just a few degrees over thousands or even millions of years. Yet in the finely balanced world of the outer core, these gentle thermal shifts trigger cascades of change that eventually influence the entire planet. To understand what happens when the core temperature drops by degrees, we need to think about how individual atoms of iron behave under these extreme conditions. Each iron atom in the liquid metal around us is in constant motion, vibrating with thermal energy that keeps the metal in its liquid state despite pressures that would crush any surface material into unrecognizable forms. These atomic movements aren't random chaos, but rather follow the fundamental principles of thermal physics that govern how matter behaves at the molecular level. When the temperature decreases, even by just a few degrees, the thermal energy available to each iron atom decreases proportionally. The atoms continue their constant dance, but with slightly less vigor, slightly less amplitude in their vibrations, slightly less freedom in their movements through the liquid matrix. This reduction in thermal motion has immediate consequences for the physical properties of the liquid metal, consequences that begin at the atomic scale but eventually propagate throughout the entire outer core system. The first and most immediate change is in the density of the liquid iron. As the atoms move less vigorously, they naturally pack together more closely, increasing the mass of metal contained in any given volume. This density increase is remarkably small, perhaps a fraction of a percent over thousands of years. But in a system where billions of tons of liquid metal are in constant motion, even tiny density changes create significant effects. The increased density affects how the liquid iron responds to the gravitational forces that help drive convection in the outer core. Denser regions of liquid become more likely to sink, while regions that remain at the previous density become relatively buoyant. This creates new patterns of gravitational instability, which can reorganize the large-scale convection patterns that were previously explored. But density isn't the only property that changes as the temperature drops. The viscosity of the liquid iron also increases, making the metal more resistant to flow and more difficult to deform in response to the forces that drive convection. Think of how honey becomes thicker and flows more slowly when it cools. The same principle applies to liquid iron in the outer core, though under conditions so extreme that the comparison seems almost quaint. The increase in viscosity has profound effects on the convection process. The thermal forces that drive the circulation of liquid metal remain essentially the same, but the resistance to flow increases, meaning that the same driving forces produce slower, more sluggish motion. Convection columns that previously rose through the outer core at certain speeds now move more slowly, taking longer to transport heat from the depths to the core mantle boundary. This slowing of convection creates a fascinating feedback effect. As the circulation becomes less efficient at transporting heat, temperatures in the deeper parts of the outer core begin to rise slightly, while temperatures near the core mantle boundary may drop more rapidly than before. This temperature redistribution can either accelerate or slow the overall cooling process, depending on how the changing thermal structure affects heat loss to the overlying mantle. The changing viscosity also affects the scale and spacing of convection patterns. In fluid dynamics, there's a delicate balance between the thermal forces that drive convection and the viscous forces that resist motion. When this balance shifts due to cooling, the preferred size and spacing of convection columns can change dramatically. Patterns that were stable for millions of years may suddenly become unstable, breaking up into smaller features or merging into larger ones. These reorganizations of convection don't happen suddenly or violently. Instead, they unfold over timescales of thousands to hundreds of thousands of years, as the slowly changing physical properties of the liquid iron gradually favor new patterns of circulation over the old ones. It's like watching a slow-motion kaleidoscope, where patterns that seem permanent and stable gradually dissolve and reform into new configurations of flow. The electromagnetic properties of the liquid iron are also affected by the temperature changes. The electrical conductivity of metals generally increases as temperature decreases, and iron in the outer core follows this same pattern. As the liquid metal cools, it becomes slightly more efficient at conducting electrical currents, which affects how the electromagnetic dynamo operates. Higher electrical conductivity means that electrical currents generated by the motion of the liquid iron can flow more easily and with less resistance. This can amplify the electromagnetic effects that create Earth's magnetic field, potentially making the dynamo more efficient at converting mechanical energy into magnetic energy. However, the increased conductivity also affects how quickly magnetic fields can change, potentially making the system more stable and less prone to fluctuations. The interplay between changing viscosity and changing electrical conductivity creates complex effects on the dynamo process. While higher conductivity might tend to strengthen the magnetic field, higher viscosity tends to slow the motions that generate the field in the first place. The net effect depends on the specific details of how these competing influences balance out in the particular conditions of the cooling outer core. As the temperature continues to drop over geological time, the boundary between the liquid outer core and solid inner core begins to respond to the changing thermal conditions. This boundary isn't fixed in space, but represents the pressure and temperature conditions where iron transitions from liquid to solid. As the outer core cools, this transition zone slowly moves outward, with liquid iron near the boundary crystallizing into solid metal and adding to the growing inner core. The process of crystallization releases what scientists call latent heat, the thermal energy that was stored in the liquid structure of the iron. This heat release partially counteracts the overall cooling, providing an additional source of thermal energy that can help sustain convection in the outer core. It's like having a slow-burning furnace that activates precisely when the system needs additional heat to maintain its circulation patterns. The growing inner core also changes the geometry of the outer core, reducing the volume available for liquid iron circulation. This geometric change can force the reorganization of convection patterns as the available space for large-scale circulation becomes progressively smaller. Convection columns that once extended from the inner core boundary to the core mantle boundary may find their preferred circulation patterns disrupted by the shrinking liquid zone. But the effects of cooling extend beyond just the physical properties of the liquid iron itself. The chemical composition of the outer core also responds to the changing temperature conditions. As iron crystallizes to form the growing inner core, lighter elements that were previously dissolved in the liquid metal become concentrated in the remaining liquid phase. These lighter elements, which may include sulfur, silicon, oxygen, hydrogen, or carbon, have their own effects on the physical properties of the liquid metal. They can change the density, viscosity, and electrical conductivity in ways that are independent of the pure temperature effects we've been discussing. The increasing concentration of light elements creates additional sources of buoyancy that can drive compositional convection, adding new complexity to the thermal circulation patterns. The compositional changes also affect the temperature at which iron crystallizes, potentially altering the growth rate of the inner core and the amount of latent heat released by the crystallization process. These chemical effects create feedback loops that can either amplify or dampen the consequences of thermal cooling, making the evolution of the outer core a richly interconnected process where thermal, mechanical, electromagnetic, and chemical effects all influence each other. As we observe these changes unfolding around us in our imaginary position within the outer core, we begin to appreciate the remarkable sensitivity of this system to even small thermal perturbations. The liquid iron that surrounds us exists in a state of delicate balance, where multiple physical processes are perfectly tuned to maintain stable convection and magnetic field generation. When cooling disturbs this balance, the system doesn't simply shut down or fail catastrophically. Instead, it gracefully adapts, finding new equilibrium states that accommodate the changed thermal conditions while maintaining its essential functions. The adaptation process reveals the fundamental resilience of the outer core system. Despite operating under conditions that seem impossibly extreme by surface standards, the liquid iron dynamo has demonstrated remarkable stability over billions of years of Earth's history. It has survived impacts from asteroids that created global environmental catastrophes, ice ages that froze much of the surface, and periods of intense volcanic activity that altered the composition of the atmosphere. Through all of these surface changes, the outer core has continued its patient circulation, its steady generation of magnetic fields, its gradual response to the ongoing cooling of the planet. The temperature changes we're exploring represent just one chapter in this long story of adaptation and persistence. The outer core has experienced many cycles of warming and cooling, acceleration and deceleration of circulation, strengthening and weakening of magnetic fields. Each cycle has brought new challenges and new solutions, new patterns of flow and new configurations of electromagnetic activity. The current epoch of gradual cooling that we're witnessing is neither the beginning nor the end of this process, but simply another phase in the long thermal evolution of our planet. The outer core will continue to cool, continue to adapt, continue to generate magnetic fields for billions of years into the future. The specific patterns of circulation and electromagnetic activity will change, but the fundamental processes will persist as long as liquid iron exists in the Earth's interior. The beauty of this system lies not just in its complexity or its stability, but in its fundamental gentleness. Despite the extreme conditions and the vast scales involved, the cooling of the outer core proceeds with patience and grace, allowing time for gradual adjustments and smooth transitions between different states. There are no violent explosions, no catastrophic failures, no sudden disruptions that threaten the continuity of the process. Instead, there's just the slow, steady progression of thermal equilibration, the patient adjustment of physical properties to changing conditions, the gradual evolution of circulation patterns in response to new thermal, chemical, and geometric constraints. It's a process that embodies some of the most fundamental principles of physics: the tendency toward thermal equilibrium, the conservation of energy, the relationship between temperature and the behavior of matter, but expressed on scales so vast and persistent that they provide a direct connection between the formation of our planet and its distant future. As the temperature continues its gradual decline over the millions of years ahead, the outer core will continue to find new ways to organize its circulation, new patterns of convection that efficiently transport heat while generating the magnetic fields that protect our planet. Each degree of cooling will bring new adaptations, new solutions to the challenge of maintaining stability and function under slowly changing conditions. The iron atoms that surround us in this imaginary space will continue their thermal dance, but with gradually decreasing vigor, gradually increasing cooperation, gradually evolving organization. The convection patterns will shift and reorganize. The electromagnetic dynamo will adapt to new operating conditions, and the boundary between liquid and solid metal will slowly advance outward as the cooling progresses. Through all of these changes, the essential character of the outer core will remain intact. It will continue to be a realm of patient circulation, of steady heat transport, of reliable magnetic field generation. The specific details will evolve, but the fundamental nature of the system, its stability, its resilience, its gentle response to changing conditions, will persist as one of the most enduring features of our planet. In the next chapter, we'll explore how these changes in the outer core begin to affect one of the most important and observable consequences of core dynamics: the magnetic field that extends from the deep interior all the way into space, creating the protective magnetosphere that shields our planet from the constant stream of charged particles flowing from the sun. As we continue our peaceful exploration of the outer core, suspended in this realm of liquid iron where temperatures exceed those at the surface of the sun, we turn our attention to one of the most remarkable and far-reaching consequences of the gentle cooling we've been observing. The magnetic field of Earth, that invisible force that guides compass needles and protects our atmosphere from solar wind, begins its existence here in the flowing metal that surrounds us, emerging from the complex dance of convection and electrical currents that we've been witnessing. The magnetic field isn't something separate from the core dynamics we've been exploring. It's an integral part of the same system, as intimately connected to the circulation of liquid iron as the warmth of a fire is connected to the flames that produce it. When the thermal conditions of the outer core change through cooling, the magnetic field responds with the same gentle persistence that characterizes all deep Earth processes, shifting and adapting over timescales that span thousands to millions of years. To understand how core cooling affects Earth's magnetic field, we need to appreciate the elegant mechanism by which moving liquid metal creates magnetic forces that can influence compass needles thousands of miles away at the surface. The process begins with the electrical conductivity of iron, that fundamental property that allows metals to carry electrical currents with remarkable efficiency. When the liquid iron moves through existing magnetic fields, whether generated by the planet's rotation, by previous dynamo activity, or by external sources like the solar wind, electrical currents are induced in the flowing metal according to the same electromagnetic principles that govern electrical generators and motors. These currents, once established, create their own magnetic fields, which in turn influence the motion of the conducting liquid, creating a self-sustaining feedback loop that can maintain magnetic activity for billions of years. The beauty of this dynamo process lies in its self-organizing nature. Unlike human-made electrical generators that require external power sources and mechanical maintenance, the geodynamo operates entirely through the interaction of natural forces: thermal convection, planetary rotation, electromagnetic induction, and gravitational effects, all working together to create and sustain magnetic fields of extraordinary stability and reach. But the dynamo is also exquisitely sensitive to the conditions under which it operates. The strength, orientation, and stability of the magnetic field depend critically on the specific patterns of convection in the outer core the speed and organization of the liquid iron circulation, and the physical properties of the conducting medium. When core cooling changes these fundamental parameters, the magnetic field responds accordingly. As we observe in the previous chapter, cooling increases the viscosity of liquid iron while also increasing its electrical conductivity. These two effects have competing influences on the dynamo process. Higher viscosity tends to slow convection and reduce the mechanical energy available for magnetic field generation, while higher conductivity makes the conversion of mechanical energy into magnetic energy more efficient. The net effect depends on which influence dominates under the specific conditions of the cooling outer core. In some scenarios, the increased conductivity more than compensates for the slower convection, leading to stronger and more stable magnetic fields. In others, the reduced vigor of circulation overwhelms the conductivity enhancement, resulting in weaker or more variable magnetic activity. The reorganization of convection patterns that accompanies core cooling also affects the spatial structure of the magnetic field. The dynamo doesn't generate a uniform magnetic field throughout the outer core, but rather creates complex three-dimensional patterns that reflect the underlying circulation geometry. When cooling changes the preferred scale and organization of convection, it simultaneously changes the characteristic patterns of magnetic field generation. These changes in field structure can manifest in several ways that eventually become observable at Earth's surface. The overall strength of the field may increase or decrease, the orientation of the magnetic poles may shift, or the degree of complexity in the field pattern may change. Some periods of core evolution favor simple, stable field configurations dominated by a strong dipole component. The familiar pattern where magnetic field lines emerge from one pole and converge on the other. Other periods favor more complex, multipolar configurations where several magnetic poles coexist and the field pattern becomes more intricate. The transition between different magnetic field states doesn't happen suddenly or catastrophically. Instead, the field evolves gradually, taking thousands to hundreds of thousands of years to shift from one stable configuration to another. During these transition periods, the field may become weaker, more variable, or more complex before settling into its new long-term pattern. One of the most dramatic but still gradual manifestations of changing core conditions is magnetic field reversal, where the north and south magnetic poles switch positions completely. These reversals have occurred hundreds of times throughout Earth's history, with the frequency and timing apparently related to the thermal and dynamic evolution of the outer core. During periods when core cooling leads to particularly unstable dynamo conditions, reversals may occur every few 100,000 years. During more stable periods, the same polarity may persist for millions of years. The reversal process itself provides a fascinating window into the deep dynamics of the outer core. Paleomagnetic studies of ancient rocks reveal that reversals don't happen instantly, but unfold over periods of several thousand years. During a reversal, the field strength typically decreases significantly. The magnetic poles may wander erratically across the surface, and complex multipolar field patterns may temporarily dominate before a new stable dipole emerges with opposite polarity. These reversal periods demonstrate the intimate connection between core cooling and magnetic field behavior. The thermal evolution that drives long-term changes in core dynamics also influences the stability and persistence of magnetic field configurations. Periods of more rapid cooling or significant reorganization of convection patterns tend to correlate with increased reversal frequency, while periods of thermal stability favor longer-lasting magnetic polarity epochs. The cooling-related changes in magnetic field strength and structure have consequences that extend far beyond the core itself. Earth's magnetic field creates a vast region of space called the magnetosphere, where the planetary magnetic field dominates over the magnetic fields carried by the solar wind. This magnetosphere acts as a protective shield, deflecting most of the charged particles streaming from the sun and preventing them from directly interacting with our atmosphere. When core cooling leads to changes in magnetic field strength, the size and effectiveness of the magnetosphere change accordingly. A stronger field creates a larger, more robust magnetosphere that provides better protection from solar wind particles. A weaker field results in a smaller magnetosphere that may allow more solar particles to penetrate closer to Earth, potentially affecting atmospheric chemistry and climate patterns. The shape and stability of the magnetosphere also respond to changes in magnetic field complexity. A simple dipole field creates a symmetric, stable magnetosphere with well-defined boundaries and predictable particle deflection patterns. More complex multipolar fields can create irregular magnetospheres with varying effectiveness in different directions, potentially allowing solar wind access to the atmosphere in some regions while maintaining strong protection in others. These magnetospheric changes can influence atmospheric processes through several mechanisms. Charged particles that penetrate the magnetosphere can interact with atmospheric gases, creating ionization, chemical reactions, and enhanced auroral activity. Changes in the amount and distribution of such interactions can affect atmospheric composition, temperature structure, and circulation patterns, potentially influencing surface climate over long timescales. The cooling of the outer core also affects more subtle aspects of magnetic field behavior that can be detected by sensitive modern instruments. The magnetic field isn't perfectly steady, but exhibits small variations and fluctuations that reflect the ongoing dynamics of the outer core. These variations, called geomagnetic secular variation, provide real-time information about changes in core circulation patterns. As core cooling progresses and convection patterns reorganize, the character of secular variation changes accordingly. Periods of vigorous, well-organized convection tend to produce smooth, predictable changes in field strength and direction. Periods when convection becomes more chaotic or transitions between different organizational states tend to produce more irregular, less predictable variations. The timescales of secular variation also reflect the changing dynamics of the cooling core. When convection becomes slower due to increased viscosity, the timescales of magnetic field changes tend to increase accordingly. Features that once changed over decades may begin to change over centuries, and the overall rate of magnetic evolution may decrease as the core dynamics become more sluggish. Modern satellite observations of Earth's magnetic field provide unprecedented detail about these ongoing changes, revealing complex patterns of strengthening and weakening, pole motion, and field complexity that reflect the current thermal state of the outer core. These observations show that the field is currently weakening in some regions while strengthening in others, with the magnetic poles moving at rates of several kilometers per year. The current pattern of magnetic field change appears consistent with the ongoing cooling and evolution of the outer core, suggesting that we may be witnessing one of the gradual transitions between different dynamo states that have occurred throughout Earth's history. The field isn't collapsing or failing, but rather adapting to slowly changing core conditions in the same way it has adapted to countless previous changes over billions of years. The relationship between core cooling and magnetic field evolution also provides insights into the future behavior of Earth's magnetic system. As cooling continues over millions of years ahead, the dynamo will continue to adapt and evolve, finding new ways to generate magnetic fields under progressively different thermal conditions. The specific details of future field behavior are difficult to predict, but the fundamental processes that create and maintain the field are expected to persist as long as liquid iron exists in the outer core. The study of magnetic fields on other planets provides additional perspective on how core cooling affects planetary magnetism. Mars, which is smaller than Earth and has cooled more rapidly, appears to have lost its global magnetic field billions of years ago when its core became too cool to sustain vigorous convection. Venus, similar in size to Earth but with different thermal evolution, has no significant magnetic field despite having a partially liquid core. These planetary comparisons suggest that the relationship between core thermal state and magnetic field generation follows similar principles throughout the solar system, with the specific outcomes depending on planet size, composition, thermal history, and rotation rate. Earth's magnetic field represents a particular solution to the challenge of maintaining dynamo activity under our planet's specific conditions. but it's part of a broader family of planetary magnetic phenomena that all respond to core thermal evolution in related ways. As we float here in our imaginary position within the outer core, we can sense the magnetic field lines being born from the motion of the liquid metal around us. These invisible lines of force emerge from the chaotic circulation of conducting iron and organize themselves into the coherent patterns that extend through the mantle, across the surface, and far into space. The field lines we're witnessing begin their journey here in the depths and end their paths in the solar wind, millions of kilometers from Earth. The gentle cooling that we've been exploring doesn't destroy this remarkable process, but rather guides its evolution toward new configurations that are equally capable of protecting our planet and maintaining the magnetic environment that has sheltered life for billions of years. The dynamo is remarkably robust and adaptive, capable of generating effective magnetic fields under a wide range of thermal conditions. The magnetic field changes associated with core cooling operate on the same patient timescales that characterize all deep Earth processes. The field that protects us today is the product of circulation patterns that developed over thousands to millions of years of gradual thermal evolution. The future field that will protect Earth millions of years from now is being shaped by the cooling processes we're observing right now. In this very moment, as thermal energy slowly leaks from the outer core toward the surface. This connection between current cooling and future magnetic protection provides a profound example of how processes operating on geological timescales create the conditions that enable life as we know it. The magnetic field that shields our atmosphere from solar wind erosion, that enables the formation of stable atmospheric chemistry, that creates the auroral displays that have inspired human wonder for millennia. All of this emerges from the patient cooling of liquid iron in the darkness miles beneath our feet. In the next chapter, we'll explore how the changing circulation patterns in the cooling outer core create new pathways for heat and momentum transport, reorganizing the three-dimensional flow structure in ways that affect everything from magnetic field generation to the transfer of angular momentum between the core and the rest of the planet. Here in the heart of our planet, surrounded by the gentle circulation of liquid iron that has continued uninterrupted for billions of years, we're about to witness one of the most elegant demonstrations of how complex systems adapt to changing conditions. As the outer core gradually cools and its physical properties slowly evolve, the grand patterns of convection that transport heat and generate magnetic fields begin to reorganize themselves, finding new pathways through the liquid metal that are perfectly suited to the altered thermal landscape. The reorganization of circulation patterns in the cooling outer core represents one of nature's most sophisticated examples of self-organization, where a system with no central control or predetermined plan manages to restructure itself in response to changing conditions while maintaining its essential functions. The liquid iron around us doesn't follow any blueprint or instruction manual as it adapts to cooling. Instead, it responds to the fundamental forces of physics in ways that naturally lead to new stable configurations. To understand how these new circulation patterns emerge, we need to appreciate the delicate balance of forces that governs convection in the outer core. The circulation we've been observing isn't driven by a single simple force, but rather emerges from the complex interaction of thermal buoyancy, gravitational effects, rotational forces, electromagnetic influences, and the physical constraints imposed by the geometry of the core itself. Thermal buoyancy provides the primary driving force for convection, as hot liquid iron near the inner core boundary becomes less dense than the cooler iron above it and begins to rise. But this simple thermal driving is complicated by the rotation of the Earth, which deflects rising and falling currents according to the Coriolis effect, creating the helical circulation patterns that are essential for magnetic field generation. Electromagnetic forces add another layer of complexity, as the magnetic fields generated by previous circulation influence the motion of the conducting liquid iron, creating feedback loops that can either enhance or suppress different types of flow. The chemical composition of the liquid metal also matters, as the concentration of lighter elements affects density and creates additional driving forces for circulation. As cooling changes the physical properties of the liquid iron, it alters the balance between all of these competing influences. The increased viscosity that accompanies cooling makes the liquid more resistant to the forces trying to drive circulation, while the changing density affects the strength of thermal buoyancy. The altered electrical conductivity changes how electromagnetic forces influence the flow, and the evolving chemical composition as the inner core grows adds new sources of buoyancy and complexity. The remarkable thing about the outer core system is how smoothly it manages these transitions. Rather than becoming unstable or chaotic when the balance of forces changes, the circulation gradually evolves toward new configurations that efficiently accommodate the altered conditions. Old patterns of flow that are no longer favored by the changing physical conditions slowly weaken and fade away, while new patterns that are better suited to the current thermal state gradually strengthen and become dominant. This transition process operates through what fluid dynamicists call mode selection, where the system naturally chooses the circulation patterns that are most stable and efficient under the current conditions. The liquid iron doesn't need to experiment with different flow patterns or learn through trial and error. The physics of fluid motion automatically favors the configurations that provide the best balance between driving forces and resistance to flow. The spatial scales of convection are particularly sensitive to changes in the thermal state of the outer core. When the liquid iron is very hot and has low viscosity, thermal forces can easily overcome viscous resistance, allowing convection to occur over a wide range of length scales. Under these conditions, the outer core may support many different convection patterns simultaneously, from small, rapid cells to large, slow circulation systems. As cooling increases the viscosity of the liquid iron, smaller scale convection becomes increasingly difficult to sustain. The thermal forces that drive circulation remain essentially the same, but the increased resistance to flow means that only the largest, most energetically favorable patterns can persist. This leads to a gradual simplification of the circulation structure, with fewer but more vigorous convection cells dominating the flow. This scale selection process has profound implications for magnetic field generation, since the characteristics of the geodynamo depend critically on the size and organization of convection patterns. Large-scale, well-organized circulation tends to produce strong, stable magnetic fields with simple dipolar structure. Smaller-scale, more complex convection may generate weaker fields with more complicated multipolar patterns. The reorganization of circulation scales as the core cools helps explain some of the long-term trends observed in Earth's magnetic field behavior. Periods of geological history when a magnetic field was particularly strong and stable may correspond to times when core cooling had progressed to the point where only large-scale, efficient convection patterns could persist. Periods of more variable or complex magnetic behavior may reflect times when the thermal state of the core supported more diverse circulation patterns. The three-dimensional structure of convection in the outer core is also affected by cooling in subtle but important ways. The circulation isn't simply two-dimensional, like weather patterns in the atmosphere, but truly three-dimensional, with complex interconnections between different parts of the outer core through vertical circulation, lateral transport, and helical flow patterns. As the physical properties of the liquid iron change with cooling, the preferred three-dimensional organization of these circulation patterns evolves accordingly. Convection columns that previously rose straight up from the inner core boundary may begin to tilt or develop helical structure. Lateral connections between different convection cells may strengthen or weaken. The overall connectivity of the circulation system may increase or decrease, depending on how cooling affects the balance between different types of flow. These changes in three-dimensional structure affect how efficiently the circulation can transport heat from the inner core to the core mantle boundary. More connected, well-organized flow patterns tend to be more efficient at heat transport, while more fragmented or chaotic patterns may be less effective. This feedback between circulation efficiency and thermal structure creates another layer of complexity in how the cooling outer core evolves over time. The temporal evolution of convection patterns also changes as the core cools. When the liquid iron has low viscosity, circulation patterns can change relatively quickly in response to small perturbations or changes in driving forces. The system is dynamically active, with convection cells forming, evolving, and disappearing over timescales of thousands to tens of thousands of years. As viscosity increases with cooling, the circulation becomes more sluggish and less responsive to short-term changes. Convection patterns that develop under these conditions tend to be more stable and longer-lasting, persisting for hundreds of thousands or even millions of years before evolving into new configurations. This increased temporal stability in circulation patterns contributes to the increased stability often observed in magnetic field behavior during certain periods of Earth's history. The chemical effects of cooling add another dimension to the reorganization of circulation patterns. As the inner core grows and lighter elements become more concentrated in the remaining liquid iron, new forms of convection can develop that are driven by compositional rather than thermal buoyancy. These compositional currents may have different preferred scales and organization than purely thermal convection, adding new complexity to the overall circulation structure. The interaction between thermal and compositional convection can create remarkably complex flow patterns, with different types of circulation occupying different regions of the outer core or operating on different timescales. Some patterns may be driven primarily by temperature differences, others by compositional variations, and still others by the interaction between thermal and chemical effects. The boundaries between different types of convection can be dynamic, shifting and evolving as the cooling progresses and the chemical composition of the outer core continues to change. These boundary dynamics add another layer of complexity to the system, creating opportunities for new types of circulation patterns to develop and for existing patterns to evolve in unexpected ways. One of the most fascinating aspects of circulation reorganization in the cooling outer core is how it affects the coupling between different parts of the Earth system. The outer core doesn't exist in isolation, but is connected to the mantle above through heat transfer and to the inner core below through thermal and chemical exchange. Changes in outer core circulation patterns can affect these connections in ways that influence the entire planet. For example, changes in the efficiency of heat transport from the core to the mantle can affect mantle convection patterns, which in turn influence plate tectonics, volcanic activity, and surface topography. Changes in the rate of inner core growth can affect the supply of light elements to the outer core, influencing the chemical driving forces for convection. These connections create feedback loops that link deep Earth processes to surface phenomena over geological timescales. The reorganization of circulation patterns also affects the transfer of angular momentum between the core and the rest of the planet. The liquid iron in the outer core doesn't rotate at exactly the same rate as the solid Earth, but is coupled to the mantle and crust through electromagnetic and gravitational forces. Changes in circulation patterns can alter this coupling, potentially affecting the length of Earth's day over long timescales. As we observe these circulation changes from our imaginary position within the outer core, we can appreciate the remarkable sophistication of the adaptive mechanisms at work. The liquid iron around us is constantly adjusting its flow patterns to maintain optimal efficiency under changing thermal conditions, finding new solutions to the challenge of heat transport that are perfectly suited to the current state of the system. The reorganization process demonstrates the fundamental stability and resilience of the outer core system. Rather than being disrupted or destabilized by cooling, the circulation simply evolves toward new configurations that work just as well under the altered conditions. The system's ability to adapt and reorganize ensures that essential functions like heat transport and magnetic field generation continue to operate effectively even as the thermal state of the core changes over geological time. The mathematical beauty of this reorganization process lies in its optimization properties. The circulation patterns that emerge from cooling aren't random or arbitrary, but represent solutions that maximize efficiency while minimizing energy dissipation. The physics of fluid motion naturally selects for patterns that accomplish the necessary heat transport with the least possible resistance, creating flow structures that are both functionally effective and energetically efficient. This optimization occurs without any external control or guidance. It's simply the natural result of physical laws operating on a complex system over long timescales. The liquid iron finds the best solutions to its transport challenges through the same fundamental principles that govern all fluid motion, but applied under the extreme conditions and vast scales of the Earth's interior. The timescales involved in circulation reorganization provide another connection to the deep rhythms of planetary evolution. The new flow patterns that we're witnessing develop don't emerge overnight, but evolve gradually over thousands to millions of years as the physical properties of the liquid iron slowly change with cooling. This gradual evolution ensures smooth transitions between different circulation states, avoiding the instabilities that might arise from rapid changes. The future evolution of outer core circulation patterns will continue to be guided by the same physical principles that have governed the system for billions of years. As cooling progresses and the thermal state of the core continues to evolve, new circulation configurations will emerge that are perfectly adapted to the conditions that exist millions of years from now. The specific details of these future patterns are difficult to predict, but their fundamental characteristics, efficiency, stability, and optimal heat transport, are guaranteed by the laws of physics. In the next chapter, we'll explore how these changes in deep Earth circulation begin to manifest themselves at the surface, creating subtle but measurable effects on magnetic field orientations, heat flow patterns, and other phenomena that provide windows into the ongoing thermal evolution of our planet's heart. As we begin our gentle ascent from the heart of our planet, leaving behind the realm of liquid iron and extreme pressures where we've witnessed the patient cooling and circulation reorganization of the outer core, we embark on a journey toward the surface to discover how these profound, deep changes eventually make themselves known to those of us who live in the world of sunlight and familiar temperatures. The effects we're about to explore represent one of the most remarkable aspects of Earth as a system. The way processes occurring thousands of miles beneath our feet can create subtle but measurable changes in the world we experience every day. The journey from the outer core to Earth's surface is itself a story of gradual transition and patient energy transfer. The changes that begin with cooling liquid iron at the center of our planet don't leap instantly to the surface, but rather propagate upward through the mantle over timescales that span thousands to millions of years, creating a chain of interconnected effects that eventually become observable in phenomena as diverse as magnetic field measurements, volcanic activity, and even the precise timing of our planet's rotation. The first and most direct surface expression of core cooling appears in the behavior of Earth's magnetic field, that invisible force that guides compass needles and protects our atmosphere from the solar wind. While the magnetic field is generated deep in the outer core by the dynamo processes we've been exploring, it extends all the way to the surface and beyond, creating a bridge between the hidden realm of the deep Earth and the familiar world where humans live and work. Modern magnetic observatories scattered across the globe continuously monitor the strength and direction of the magnetic field with extraordinary precision. These measurements reveal a constantly changing magnetic environment, with variations that occur over timescales ranging from seconds to centuries. While some of these variations are caused by external influences like solar storms and atmospheric currents, others reflect the ongoing evolution of conditions deep within the outer core. The long-term trends in magnetic field measurements provide some of the clearest evidence for the effects of core cooling at Earth's surface. Over the past several centuries, detailed records show systematic changes in magnetic field strength and orientation that appear to reflect the gradual reorganization of circulation patterns in the cooling outer core. These changes don't happen suddenly or dramatically, but unfold with the same patient persistence that characterizes all deep Earth processes. One of the most obvious manifestations of changing core conditions is the movement of the magnetic poles. The locations where the magnetic field lines are vertical, the magnetic north and south poles, aren't fixed points on Earth's surface, but rather move continuously as the underlying dynamo structure evolves. Over the past century, the magnetic North Pole has been moving across the Arctic at an accelerating pace, traveling hundreds of miles as the circulation patterns in the outer core slowly reorganize. This pole movement isn't random wandering, but rather reflects systematic changes in the three-dimensional structure of the magnetic field generated by the cooling core. As circulation patterns in the outer core find new pathways and organizations, the magnetic field they generate develops new centers of intensity and new orientations that manifest as moving magnetic poles of the surface. The rate of pole movement has been increasing in recent decades, suggesting that the outer core may currently be undergoing a period of relatively rapid transition between different circulation states. This acceleration doesn't indicate any catastrophic change in the core, but rather reflects the ongoing adaptation of the dynamo system to slowly evolving thermal conditions. Changes in magnetic field strength provide another window into the deep thermal evolution of our planet. Different regions of Earth's surface experience different trends in magnetic intensity, with some areas showing strengthening fields while others show weakening. These regional variations reflect the complex three-dimensional structure of circulation reorganization in the outer core, where some convection patterns may be strengthening while others weaken or change their organization. The overall global magnetic field strength has been declining for the past several centuries, dropping by about 10% since detailed measurements began. This decline appears to be part of a longer-term trend that may reflect the gradual cooling and changing circulation efficiency of the outer core. However, similar declines have occurred in the past and have been followed by periods of strengthening, suggesting that the current trend is part of the natural variability of the dynamo system rather than a sign of impending magnetic field collapse. The complexity of magnetic field variations at the surface reflects the sophisticated three-dimensional circulation patterns we observed in the outer core. Instead of simple, uniform changes, the magnetic field exhibits intricate patterns of strengthening and weakening, rotation and translation, that mirror the complex reorganization of convection in the deep interior. These patterns can be mapped and analyzed to infer details about circulation changes that are occurring thousands of miles beneath the surface. Satellite measurements of the magnetic field provide unprecedented detail about these ongoing changes, revealing features and variations that would have been impossible to detect from ground-based observations alone. The European Space Agency's SWARM mission, for example, has mapped the magnetic field with such precision that scientists can track changes occurring over periods as short as a few months, providing real-time observations of the dynamic evolution of the geodynamo. These high-precision measurements reveal that the magnetic field is far from static, but rather exhibits complex patterns of change that appear to reflect ongoing circulation reorganization in the outer core. Regions of rapidly changing magnetic intensity, areas where the field direction is rotating, and zones where new magnetic features are appearing or disappearing all provide evidence for the dynamic evolution of the deep dynamo system. But magnetic field changes aren't the only surface manifestation of core cooling. The heat flow from the Earth's interior also reflects the thermal evolution of the deep interior, though these effects are much more subtle and difficult to detect than magnetic variations. As circulation patterns in the outer core reorganize and heat transport efficiency changes, the amount of thermal energy reaching the core mantle boundary may vary, eventually affecting the temperature structure of the mantle and the amount of heat reaching the surface. These thermal effects operate on much longer timescales than magnetic changes, since heat takes much longer to propagate through the solid mantle than magnetic field changes take to propagate through the same region. Changes in heat flow patterns that result from core cooling may take millions of years to become apparent at the surface, but they can eventually influence phenomena like volcanic activity, mantle convection patterns, and even the formation and destruction of mountain ranges. The study of ancient volcanic rocks provides one approach to detecting these long-term thermal effects. Volcanic eruptions bring material from the deep mantle to the surface, carrying with them chemical and thermal signatures that reflect the conditions deep within the Earth at the time of eruption. By analyzing the chemistry and temperature history of ancient volcanic rocks, scientists can reconstruct the thermal evolution of the mantle and potentially detect the influence of changing core conditions over geological timescales. The relationship between core cooling and surface volcanism is complex and indirect, involving multiple stages of heat transfer and chemical processing as thermal energy moves from the core through the mantle to the surface. Changes in core heat output don't directly cause volcanic eruptions, but they may influence the long-term thermal structure of the mantle in ways that affect the frequency, intensity, or chemical composition of volcanic activity over millions of years. Another surface manifestation of core cooling appears in subtle changes to Earth's rotation. The liquid iron in the outer core doesn't rotate at exactly the same rate as the solid Earth, and changes in circulation patterns can affect the transfer of angular momentum between the core and the rest of the planet. These effects are extremely small, but they can be detected by precise astronomical observations that measure tiny variations in the length of Earth's day. Over the past several decades, measurements have revealed small but systematic changes in Earth's rotation rate that appear to correlate with changes in the magnetic field, suggesting a common origin in the evolving dynamics of the outer core. These rotational variations amount to just a few milliseconds per day, but they provide another independent line of evidence for ongoing changes in the deep interior. The precision required to detect these rotational effects is truly remarkable. Modern astronomical techniques can measure changes in Earth's rotation to the level of microseconds, revealing variations so small that they would be completely imperceptible to human senses, but significant enough to provide insights into deep Earth processes. These measurements represent one of the most sophisticated examples of how modern science can detect the surface consequences of processes occurring thousands of miles beneath our feet. The coupling between core circulation and Earth's rotation also works in reverse, with changes in rotation rate potentially affecting circulation patterns in the outer core. This creates another feedback loop connecting surface phenomena to deep Earth processes, where variations in rotation caused by atmospheric, oceanic, or astronomical effects can influence the thermal and dynamic evolution of the core over long timescales. Changes in the Earth's gravitational field provide yet another surface manifestation of deep cooling processes. As circulation patterns in the outer core reorganize and the inner core continues to grow, the distribution of mass within the Earth changes very slightly. These changes are far too small to affect everyday phenomena like the weight of objects or the behavior of falling bodies, but they can be detected by sensitive satellite measurements that monitor tiny variations in Earth's gravitational field. The GRACE satellite mission, for example, has mapped Earth's gravitational field with such precision that it can detect the movement of water masses in the atmosphere and oceans. While most of the gravitational variations that GRACE observes are caused by surface processes like changes in ice sheet mass or groundwater levels, some of the longer-term trends may reflect deep Earth processes like core cooling and mantle circulation changes. The detection of gravitational signals from deep Earth processes represents one of the frontier areas of geophysics, where scientists are working to separate the effects of surface changes from the subtle signatures of deep interior evolution. As measurement techniques continue to improve, it may become possible to directly monitor the thermal evolution of the core through its gravitational effects, providing yet another window into the deep processes we've been exploring. The integration of all these different types of surface observations, magnetic field measurements, heat flow studies, rotational variations, and gravitational changes, creates a comprehensive picture of how deep Earth processes manifest themselves in the observable world. Each type of measurement provides different information about the cooling and evolution of the outer core, and together they create a detailed portrait of our planet's ongoing thermal evolution. The remarkable thing about these surface manifestations is how they demonstrate the fundamental interconnectedness of Earth as a system. Processes that begin with the cooling of liquid iron thousands of miles beneath the surface eventually influence phenomena that we can observe and measure in laboratories and observatories around the world. This connection between the deepest interior and the surface environment shows how Earth functions as an integrated system, where changes in one component eventually affect all others. The timescales involved in these surface manifestations provide another perspective on the nature of geological time. While magnetic field changes can be observed over periods of years to centuries, thermal effects may take millions of years to propagate from the core to the surface. Rotational and gravitational effects operate on intermediate timescales, creating a spectrum of observable phenomena that span the full range of geological time. This spectrum of timescales means that scientists studying core cooling must integrate observations over vastly different temporal ranges, from real-time satellite measurements to geological records spanning millions of years. The challenge is to identify the common threads that connect short-term variations to long-term trends, recognizing the signatures of deep cooling processes across all these different timescales. The surface manifestations of core cooling also provide a unique opportunity to test our understanding of deep Earth processes. The magnetic field changes, thermal effects, and rotational variations that we observe at the surface can be compared to predictions based on models of core cooling and circulation reorganization. When observations match predictions, it strengthens our confidence in our understanding of deep Earth processes. When they don't match, it reveals new aspects of the system that require further investigation. As we stand here at Earth's surface, looking down toward the hidden realm where liquid iron circulates in the darkness thousands of miles below, we can appreciate the remarkable sensitivity of modern science to the subtle effects of deep Earth processes. The instruments and techniques that allow us to detect these surface whispers of deep changes represent some of the most sophisticated achievements of human technology, capable of measuring variations so small that they reveal the secrets of our planet's most hidden realm. In the next chapter, we'll delve deeper into the physical properties of cooling metals, exploring how the slowing dance of iron and nickel atoms creates the cascade of changes that we've been tracing from the molecular level to the planetary scale. As we return once more to the heart of our planet, drawn back to that realm of liquid iron, where temperatures exceed those at the surface of the sun and pressures crush matter into configurations that exist nowhere else in our solar system, we turn our attention to the most fundamental level of the cooling process, the behavior of individual atoms as they respond to the gradual decrease in thermal energy that drives all the changes we've been exploring. Here, suspended in our imagination within the outer core, we're surrounded by countless trillions of iron and nickel atoms, each one participating in a dance of thermal motion that has continued for over 4 billion years. These atoms don't exist as isolated particles, but rather as part of a complex liquid structure where each atom is constantly interacting with its neighbors through electromagnetic forces, forming temporary bonds that break and reform millions of times per second in the fluid choreography of metallic liquid. The dance of these atoms is driven by thermal energy, the kinetic energy of motion that we experience as temperature. Each atom vibrates, rotates, and translates through the liquid medium with energy that's directly proportional to the temperature of the system. When the outer core was hotter in the past, this atomic dance was more vigorous, more chaotic, more energetic. As cooling progresses, the dance gradually slows, becomes more constrained, more organized. This slowing isn't uniform or simple, but follows the complex rules of quantum mechanics and statistical physics that govern how matter behaves at the atomic scale. Iron atoms in the extreme environment of the outer core don't behave exactly like iron atoms in familiar surface conditions. The enormous pressures compress the electron clouds that surround each atomic nucleus, altering the chemical bonds and electromagnetic interactions that determine how the atoms move and interact with each other. Under the conditions that exist in the outer core, iron exists in what material scientists call a close-packed liquid structure, where atoms are arranged as efficiently as possible given the constraints of thermal motion and electromagnetic repulsion. The atoms pack together more densely than they would under surface conditions, creating a liquid that's about 3 times denser than water despite being composed of relatively light metallic elements. As cooling progresses and thermal energy decreases, the atoms in this closed-packed structure have less freedom to move and vibrate. The thermal forces that keep them in constant motion become weaker relative to the electromagnetic forces that tend to pull them into more organized arrangements. This creates a gradual transition toward more structured, more ordered configurations that affect every aspect of how the liquid metal behaves. The viscosity changes that we've discussed in previous chapters arise directly from this atomic level slowing. When atoms move more slowly and have less thermal energy to overcome the electromagnetic attractions between them, they become more reluctant to flow past each other when the liquid is subjected to shearing forces. It's like the difference between a dance where everyone is moving vigorously and independently versus one where the dancers are moving more slowly and are more likely to coordinate their movements with their partners. This atomic level perspective on viscosity helps explain why the changes are so gradual and predictable. The viscosity of liquid iron doesn't change suddenly or erratically as cooling progresses, but rather follows smooth mathematical relationships that reflect the underlying statistical behavior of vast numbers of atoms. Each individual atom may move somewhat randomly, but the collective behavior of trillions of atoms creates predictable bulk properties that change smoothly with temperature. The electrical conductivity changes that affect magnetic field generation also arise from atomic-level processes, specifically the behavior of electrons that can move freely through the metallic structure. In metals, some electrons aren't bound to specific atoms, but rather form what physicists call an electron sea, a cloud of mobile charge carriers that can move through the material in response to electric and magnetic fields. As cooling progresses, the atomic structure becomes more organized and the pathways for electron movement become more efficient. The electrons encounter less resistance as they move through the liquid metal, leading to higher electrical conductivity. This improvement in conductivity with cooling is one of the fundamental properties of metals, and it plays a crucial role in how the electromagnetic dynamo responds to changing thermal conditions. The relationship between atomic motion and electrical conductivity reveals one of the most elegant aspects of metallic behavior. The same thermal motion that gives liquid iron its fluid properties also creates obstacles for electron movement. As cooling reduces thermal motion, it simultaneously makes the liquid more viscous, resistant to mechanical flow, while making it more conductive, less resistant to electrical flow. These competing effects create the complex balance of properties that determines how the geodynamo evolves as the core cools. The behavior of nickel atoms in the liquid iron adds another layer of complexity to the atomic dance. Nickel makes up about 10% of the outer core's composition, and its presence significantly affects the properties of the liquid metal. Nickel atoms are slightly smaller than iron atoms, and they have different electromagnetic properties that alter how the liquid responds to cooling. The interaction between iron and nickel atoms creates what material scientists call an alloy, where the properties of the mixture are different from those of either pure component. The iron-nickel alloy that makes up the outer core has enhanced electrical conductivity compared to pure iron, better resistance to certain types of structural changes, and modified thermal properties that affect how efficiently heat can be transported through the liquid. As cooling progresses, the iron-nickel alloy undergoes subtle changes in its atomic level organization. The relative arrangement of iron and nickel atoms may shift to favor configurations that are more stable at lower temperatures. These structural changes don't alter the fundamental liquid nature of the outer core, but they do fine-tune its physical properties in ways that affect circulation patterns and magnetic field generation. The presence of light elements, sulfur, silicon, oxygen, hydrogen, or carbon, adds yet another dimension to the atomic dance. These elements exist in much smaller concentrations than iron and nickel, but their influence on atomic level behavior is significant. Light elements tend to occupy specific positions in the liquid structure, creating local variations in density and electromagnetic properties that affect how the liquid responds to thermal changes. As the inner core grows and light elements become more concentrated in the remaining liquid, the atomic structure of the outer core gradually evolves toward compositions that have never existed before in Earth's history. This compositional evolution creates new atomic arrangements and new physical properties that guide the continuing thermal evolution of the core in directions that are determined by the fundamental physics of metallic liquids. The quantum mechanical nature of atomic behavior becomes particularly important under the extreme conditions of the outer core. At the pressures and temperatures that exist thousands of miles beneath the surface, the normal rules of chemistry are modified by quantum effects that don't occur under surface conditions. Electron orbitals are compressed, chemical bonds are strengthened or weakened in unexpected ways, and new types of atomic interactions become possible. These quantum effects influence how atoms respond to cooling in ways that can't be predicted from surface experiments or simple extrapolations. The atomic dance in the outer core follows rules that are unique to the extreme environment of the deep Earth, creating behaviors and properties that exist nowhere else in our solar system, except perhaps in the cores of other terrestrial planets. One of the most remarkable aspects of atomic behavior in the cooling outer core is how it maintains liquid structure even as thermal energy decreases. Under surface conditions, cooling iron would eventually reach a freezing point where it would crystallize into solid metal. But in the outer core, the enormous pressure raises the melting temperature so high that the iron remains liquid even as it cools. This pressure-enhanced stability of the liquid state is crucial for maintaining the circulation and magnetic field generation that characterize the outer core. If cooling caused widespread solidification, the convection patterns we've been exploring would be disrupted and the geodynamo would cease to operate. Instead, the atomic structure adapts to lower temperatures while maintaining its essential liquid character, ensuring the continuity of core dynamics over geological time. The atomic-level perspective also reveals why core cooling is such a gradual, predictable process. The thermal energy that drives atomic motion doesn't disappear suddenly, but rather leaks away slowly through the complex process of heat conduction through the mantle and radiation to space. Each atom loses thermal energy at essentially the same rate, creating a uniform cooling process that affects the entire outer core simultaneously. This uniform cooling creates remarkably stable conditions for the gradual evolution of atomic arrangements and physical properties. There are no sudden temperature drops or rapid changes that might destabilize the liquid structure or create chaotic responses in the circulation patterns. Instead, the atomic dance slows down gradually and predictably, allowing the complex systems built on atomic behavior — viscosity, conductivity, density, convection, magnetic field generation — to adapt smoothly to changing conditions. The study of atomic behavior under extreme conditions has revealed that the cooling process actually enhances some aspects of the atomic dance while constraining others. As thermal energy decreases, individual atomic motions become less random and more correlated with the movements of neighboring atoms. This increased correlation leads to more efficient heat transport in some directions and more organized electromagnetic responses. The enhanced atomic correlation that develops with cooling helps explain why the outer core becomes more efficient at certain processes even as others slow down. The magnetic field generation process, for example, may become more efficient as atomic-level electrical conductivity improves, even though the overall circulation becomes more sluggish. This balance between enhanced efficiency and reduced vigor creates the complex evolutionary pathways that characterize long-term core behavior. Temperature changes in the outer core also affect the vibrational modes of iron and nickel atoms, the specific ways that atoms oscillate around their average positions in the liquid structure. As cooling progresses, some vibrational modes become more prominent while others are suppressed, creating changes in thermal and mechanical properties that propagate through the entire circulation system. These vibrational effects create another connection between atomic-level processes and planetary-scale phenomena. The specific frequencies at which atoms vibrate can affect how efficiently heat is transported, how quickly viscosity changes with temperature, and how strongly the liquid couples to magnetic fields. Changes in atomic vibrations that occur over thousands of years of cooling can eventually influence magnetic field behavior observed at Earth's surface. The interaction between different types of atoms in the outer core creates complex vibrational patterns that depend on temperature, pressure, and composition. Iron atoms vibrate differently than nickel atoms, and the presence of light elements creates additional vibrational modes that weren't present in the original iron-nickel alloy. These multi-component vibrational systems create rich spectra of atomic motion that evolve continuously as cooling progresses. The atomic dance of cooling metals in the outer core represents one of the most sustained and stable physical processes in our solar system. The same fundamental atomic interactions that we can study in laboratory metals operate in the outer core, but under conditions so extreme and over timescales so vast that they create phenomena without parallel in human experience. As we observe this atomic dance from our imaginary position within the outer core, we can appreciate how the most fundamental level of physical reality, the behavior of individual atoms, connects directly to the largest scale phenomena we've been exploring. The magnetic field that protects our atmosphere, the circulation patterns that transport heat through the planet's interior, the thermal evolution that connects Earth's formation to its distant future. All of these grand processes emerge from the simple fact that iron and nickel atoms are gradually slowing down their thermal dance in response to the patient cooling of our planet. The beauty of this atomic perspective lies in its universality. The same principles that govern atomic behavior in the outer core also operate in every piece of metal on Earth's surface, in every star in the galaxy, in every planet orbiting every star throughout the universe. The atomic dance we're witnessing represents the application of fundamental physical laws under the specific conditions that exist in Earth's interior, but the underlying principles are universal features of how matter behaves throughout the cosmos. In the next chapter, we'll explore how the atomic-level changes we've been observing eventually influence planetary-scale phenomena like Earth's rotation, its internal structure, and the long-term rhythms that connect our planet's deep interior to its surface environment and its position in the solar system. As we expand our perspective from the atomic dance of individual iron and nickel atoms to embrace the entire planet that contains them, we begin to discover how the gentle cooling of Earth's core creates ripple effects that extend far beyond the boundaries of the outer core itself. The changes we've been exploring in the depths don't remain confined to that hidden realm, but rather propagate through the entire Earth system, influencing phenomena as diverse as the length of our days, the wobble of our planet's axis, and the deep structural relationships between different layers of our world. The most immediate planetary-scale effect of core cooling appears in the subtle but measurable changes to Earth's rotation. Our planet doesn't spin in perfect isolation, but rather as part of a complex system where the liquid iron of the outer core, the solid rock of the mantle and crust, and even the atmosphere and oceans all interact through gravitational, electromagnetic, and frictional forces. When cooling changes the circulation patterns in the outer core, it alters these interactions in ways that can eventually affect how quickly our planet turns on its axis. The connection between core dynamics and planetary rotation operates through what scientists call angular momentum transfer. Angular momentum is a fundamental property of rotating systems. It represents the tendency of spinning objects to continue spinning at constant rates unless acted upon by external forces. In the Earth system, different components, the solid Earth, the liquid outer core, the atmosphere, and the oceans, can exchange angular momentum with each other, causing some parts to speed up while others slow down. The liquid iron in the outer core doesn't rotate at exactly the same rate as the solid Earth. Instead, it spins independently, driven by the same convection processes we've been exploring, but coupled to the rest of the planet through electromagnetic forces created by the interaction between the geomagnetic field and the conducting mantle. This coupling isn't rigid like the connection between gears in a machine, but rather resembles the interaction between magnetic clutches that can slip and adjust their relative motion. When core cooling changes the circulation patterns in the outer core, it affects the strength and character of this electromagnetic coupling. Changes in convection can alter the magnetic field structure in ways that modify how efficiently angular momentum is transferred between the core and the mantle. These changes don't happen suddenly, but accumulate over years to decades, creating gradual shifts in the rotation rates of different parts of the Earth system. The effects on day length are remarkably small by human standards. We're talking about changes measured in milliseconds over periods of years or decades. A day that's a few milliseconds longer or shorter than the standard 24 hours will be completely imperceptible to human senses. But these tiny variations can be detected by precise astronomical observations that monitor Earth's rotation relative to distant stars and quasars. Modern space geodesy techniques can measure changes in day length to the level of microseconds, revealing variations so small that they require the most sophisticated timing systems humans have ever developed. These measurements show that Earth's rotation is constantly changing in response to a variety of influences, including atmospheric circulation patterns, ocean currents, groundwater changes, and the deep processes we've been exploring in the outer core. The correlated variations in day length follow patterns that correlate with observed changes in the magnetic field, providing independent confirmation that both phenomena arise from common processes in the cooling outer core. When magnetic field measurements indicate that circulation patterns are reorganizing, rotation measurements often show corresponding changes in day length that support the interpretation of evolving core dynamics. But the effects of core cooling on planetary rotation extend beyond simple changes in day length. The cooling process also influences the more complex rotational motions that characterize Earth's orientation in space. Our planet doesn't spin like a perfect top, but rather wobbles slightly as it rotates, with the axis of rotation tracing small circles relative to the solid Earth over periods of about 14 months. This wobbling motion, called the Chandler wobble, is caused by the fact that Earth isn't perfectly symmetric in its mass distribution. Irregularities in the way mass is distributed throughout the planet create small departures from perfect rotational balance, leading to the complex motions that characterize real planetary rotation. Changes in the mass distribution within the Earth, including changes caused by evolving circulation patterns in the outer core, can affect the amplitude and period of these wobbling motions. Core cooling contributes to changes in Earth's mass distribution through several mechanisms. As the inner core grows and the outer core circulation patterns reorganize, the distribution of density within the planet changes very slightly. These changes are far too small to affect phenomena like surface gravity or orbital mechanics, but they're large enough to influence the precise details of rotational motion when integrated over the entire planet. The growing inner core represents a particularly important contribution to changing mass distribution. As liquid iron crystallizes to form the solid inner core, it becomes about 10% denser than the liquid from which it formed. This densification represents a slow but steady redistribution of mass toward Earth's center, affecting the planet's moment of inertia, the rotational property that determines how easily spinning objects can change their rotation rate. As the moment of inertia decreases due to inner core growth, Earth's rotation tends to speed up slightly, according to the same principle that causes figure skaters to spin faster when they pull their arms closer to their bodies. This effect is extraordinarily small. The acceleration amounts to a fraction of a millisecond per century, but it represents a measurable consequence of core cooling that will continue for billions of years as the inner core continues to grow. The redistribution of mass associated with core cooling also affects Earth's gravitational field in ways that can be detected by sensitive satellite measurements. As we discussed in the previous chapter, changes in the internal mass distribution create tiny variations in gravitational strength that can be mapped by missions like GRACE and its successors. These gravitational changes provide another independent line of evidence for ongoing core evolution. The coupling between the core and the rest of the Earth system also affects how our planet responds to external forces that tend to change its rotation. Tidal forces from the moon and sun, atmospheric pressure variations, and seasonal changes in water distribution all create torques that would change Earth's rotation if the planet were a rigid body. But Earth isn't rigid. It's a complex system with internal degrees of freedom that can absorb and redistribute these external influences. The liquid outer core plays a crucial role in this internal flexibility, acting like a vast flywheel that can store and release rotational energy in response to external perturbations. When atmospheric winds speed up and try to slow down the solid Earth's rotation, the core can compensate by spinning faster, maintaining the overall stability of the Earth system. When seasonal melting and freezing change the distribution of water between ice sheets and oceans, the core can adjust its circulation to help maintain rotational equilibrium. As core cooling changes the physical properties of the liquid iron, it affects how efficiently this rotational buffering operates. Changes in viscosity alter how quickly the core can respond to external torques, while changes in magnetic coupling strength affect how effectively angular momentum can be transferred between the core and the rest of the planet. These modifications to Earth's internal rotational dynamics create subtle but measurable changes in how our planet responds to external influences. The thermal evolution of the core also affects the deep structural relationships within the Earth system. As cooling progresses and circulation patterns reorganize, the efficiency of heat transport from the core to the overlying mantle changes in ways that can affect mantle convection patterns. These changes operate on timescales of millions of years, but they represent fundamental modifications to how Earth functions as a thermal system. Changes in core heat flux can affect the vigor and organization of mantle convection, which in turn influences phenomena like plate tectonics, volcanic activity, and mountain building. While these connections operate over geological timescales and are difficult to observe directly, they represent some of the most profound ways that core cooling affects the entire planet system. The mantle convection patterns that drive plate tectonics depend on thermal energy supplied from both the cooling core below and radioactive decay within the mantle itself. Changes in the core contribution to this thermal budget can shift the balance between different types of mantle convection, potentially affecting the speed of plate motion, the intensity of volcanic activity, and the efficiency of heat loss to space. These thermal effects create feedback loops that connect core cooling to surface processes over geological time. Changes in mantle convection can affect how efficiently heat is extracted from the core, potentially influencing the rate of core cooling itself. Variations in volcanic activity can change atmospheric composition and surface temperature, which can affect ocean circulation and ultimately influence the thermal boundary conditions for mantle convection. The magnetic field changes associated with core cooling also create connections between deep Earth processes and the space environment around our planet. As we explored in previous chapters, the magnetic field creates the magnetosphere that protects Earth from solar wind particles. Changes in field strength and structure affect the size and shape of this protective region, potentially influencing atmospheric chemistry and climate over long time scales. The magnetosphere isn't just a passive shield, but rather an active system that processes solar wind energy and redistributes it in complex patterns around Earth. Changes in magnetic field strength and organization can affect how efficiently this processing occurs, potentially altering the pathways by which solar energy reaches the upper atmosphere and influences atmospheric circulation patterns. The coupling between magnetic field changes and atmospheric processes operates through the complex physics of plasma interactions in the upper atmosphere. When charged particles from the solar wind interact with Earth's magnetic field and atmosphere, they create auroral displays, ionospheric disturbances, and upper atmospheric heating that can influence weather patterns and atmospheric circulation. Long-term changes in magnetic field strength can affect the intensity and distribution of these interactions, creating potential connections between core cooling and surface climate. The orbital dynamics of our planet also respond subtly to the internal changes associated with core cooling. Earth's orbit around the Sun isn't perfectly stable, but rather exhibits small variations caused by gravitational interactions with other planets, changes in the Sun's energy output, and the internal dynamics of Earth itself. While the internal contributions to orbital changes are much smaller than external gravitational effects, they represent measurable consequences of core evolution over geological time. The changing mass distribution within Earth as the core cools and the inner core grows affects the planet's response to tidal forces from the moon and sun. These tidal forces not only create ocean tides, but also deform the solid Earth slightly, creating complex patterns of stress and strain that depend on the internal structure and properties of our planet. Changes in core properties can affect how efficiently these tidal forces are dissipated, potentially influencing the long-term evolution of Earth's orbit and rotation. The Moon's orbit is also affected by tidal interactions with Earth, and changes in Earth's internal structure can influence the rate at which the Moon is gradually spiraling away from our planet. This orbital evolution operates over timescales of millions to billions of years, but it represents another connection between core cooling and the large-scale dynamics of the Earth-Moon system. As we contemplate these planetary-scale effects of core cooling from our perspective within the outer core, we can appreciate the remarkable interconnectedness of Earth as a system. The atomic-level changes in iron and nickel behavior that we explored in the previous chapter eventually propagate through circulation reorganization, magnetic field evolution, thermal redistribution, and rotational coupling to affect phenomena as diverse as day length, climate, plate tectonics, and orbital dynamics. The timescales involved in these planetary adjustments span the full range of geological time, from rapid magnetic field variations that could be observed over human lifetimes to thermal and structural changes that unfold over millions of years. This spectrum of timescales creates a complex web of interactions where short-term changes in core dynamics can influence long-term planetary evolution, while long-term structural changes can affect short-term variations in observable phenomena. The beauty of these planetary rhythms lies in their demonstration of how local changes can have global consequences and how processes operating on vastly different timescales can be intimately connected through the complex physics of planetary systems. The cooling of liquid iron in the outer core represents a local change in the thermal state of one component of the Earth system, but its consequences eventually reach every other component of the system, creating a symphony of planetary adjustments that will continue for billions of years. In our next chapter, we'll explore how these planetary scale changes eventually affect the most complex system we know of on Earth, the intricate web of life that has evolved on our planet's surface and depends in countless subtle ways on the stable operation of the deep Earth processes we've been exploring. As we emerge from the depths of our exploration into Earth's cooling core and begin to consider the surface world where life flourishes in countless forms, we discover one of the most remarkable aspects of our planet's thermal evolution: how the gentle, patient cooling that occurs thousands of miles beneath our feet has created the stable conditions that allow complex life to thrive over geological time. The cooling core doesn't threaten life or create instability, but rather contributes to the deep environmental stability that has enabled billions of years of evolutionary development. The magnetic field generated by the cooling core, dynamo, represents perhaps the most direct and essential connection between deep Earth processes and the existence of life as we know it. Without the protective magnetosphere created by this field, Earth's atmosphere would be gradually stripped away by the solar wind, much as appears to have happened to Mars billions of years ago. The slow evolution of the magnetic field as the core cools doesn't weaken this protection, but rather guides its adaptation to changing conditions while maintaining its essential protective function. Life on Earth has evolved under the influence of a magnetic field that has been slowly changing throughout the entire history of biological evolution. The magnetic reversals, intensity variations, and structural changes that we've explored in previous chapters have all occurred while life was present on our planet, and living systems have adapted to these changes as naturally as they've adapted to ice ages, changing atmospheric composition, and continental drift. The gradual nature of core cooling ensures that magnetic field changes never happen quickly enough to disrupt biological systems catastrophically. Even magnetic reversals, which represent some of the most dramatic changes in Earth's magnetic environment, unfold over thousands of years, timescales that allow species to adapt, migrate, or evolve new strategies for coping with altered magnetic conditions. Some species have evolved remarkable sensitivity to magnetic fields, using them for navigation during long-distance migrations. Birds, sea turtles, salmon, and many other animals appear to possess biological compasses that can detect the direction and intensity of Earth's magnetic field with extraordinary precision. The slow evolution of the magnetic field as the core cools has provided a stable navigational reference that has enabled the development of these sophisticated biological systems. The cooling of the core also affects climate and environmental conditions through its influence on atmospheric processes and ocean circulation. Changes in the magnetic field can alter the penetration of cosmic radiation into the atmosphere, potentially affecting cloud formation, atmospheric chemistry, and climate patterns over long timescales. These effects are subtle and operate through complex interactions, but they represent another pathway by which deep Earth processes can influence the surface environment where life exists. The thermal evolution of the mantle driven by core cooling affects volcanic activity and plate tectonics, which in turn influence global climate through the release of greenhouse gases, the formation of mountain ranges that affect atmospheric circulation, and the cycling of materials between the surface and the deep interior. These geological processes operate on timescales of millions of years, but they create the changing environmental conditions that drive long-term evolutionary change. The stability provided by core cooling processes has been essential for the development of complex life. The continuous operation of the geodynamo for billions of years has maintained atmospheric protection, while the gradual nature of thermal evolution has avoided catastrophic changes that might have prevented the slow development of increasingly sophisticated biological systems. As our journey through the cooling heart of our planet draws toward its gentle conclusion, we find ourselves suspended not just in the liquid iron of the outer core, but in the vast currents of geological time itself. The processes we've explored, from the atomic dance of cooling metals to the planetary rhythms that affect our entire world, all operate on timescales so vast that they provide a profound perspective on the nature of change, stability, and the deep patterns that govern our universe. The cooling of Earth's core represents one of the longest continuous processes in our solar system, a thermal evolution that began over 4.5 billion years ago when our planet first formed from the collision of countless smaller bodies in the early solar system. Since that violent beginning, the core has been cooling steadily and patiently, releasing its primordial heat to space through the gentle processes we've been exploring together. This cooling will continue for billions of years into the future, long after our sun has aged and changed, long after the surface of our planet has been transformed by forces we can barely imagine. The liquid iron that surrounds us in our imagination will continue its slow thermal dance, gradually giving up its heat to the patient embrace of space, until eventually, billions of years from now, it too will solidify and join the growing inner core. But this distant future solidification doesn't represent an ending, but rather another phase in the eternal process of planetary evolution. Even when the outer core has completely solidified, the inner core will continue to cool, the mantle will continue to convect, and Earth will continue to radiate heat to space for trillions of years beyond that point. The beauty of geological time lies in its demonstration of persistence and gradual change. The processes we've explored don't rush toward their conclusions, but rather unfold with infinite patience, allowing time for adaptation, for evolution, for the development of complexity and beauty that would be impossible on shorter timescales. The cooling core teaches us about the deep rhythms of the universe, the slow heartbeat of planetary evolution that connects the formation of worlds to their distant futures. As we drift here in this peaceful realm of liquid metal and gentle heat, we can feel ourselves connected to these vast rhythms of cosmic time. We're part of a process that began before life existed on Earth and will continue long after our species has evolved into forms we can't yet imagine. The cooling that surrounds us links us to the birth of our solar system and extends our perspective toward futures that span the lifetime of stars. Thank you for joining me on this peaceful journey into the heart of our world. If these gentle explorations of deep Earth processes have brought you comfort, if the wonder of planetary evolution has helped ease you toward rest, I'd be grateful if you'd consider subscribing to Whispering Atom. Share your thoughts in the comments. Where in the world are you drifting off to sleep tonight? And what aspects of our planet's slow thermal evolution spoke most peacefully to your mind? Sleep well, fellow traveler through geological time. Let the patient cooling of iron and nickel slow your thoughts. Let the gentle circulation of the outer core guide your breathing into deeper rhythms. Let the vast timescales of planetary evolution carry you into dreams as enduring as the slow heartbeat of our cooling world, as peaceful as the eternal dance of atoms in the darkness miles beneath your rest.